So section 3.1, linear models. In this section, we're going to go back and solve the models that we presented back in 1.3, which most of the cases were all linear or separable. One of the ways we can solve those, actually we can use either of those techniques. Recall the initial value problem for our population dynamics problem. And actually it was the same model for radioactive decay. The only difference was the sign of the parameter, the proportionality constant in the problem. Radioactive decay. Right, so I'm going to summarize it in one way. We did dp dt. The rate of change of the population, the rate of growth, was proportional to the population. So the bigger it was, the faster it grew, which means we had kp, where p at x naught, actually we even almost always, for population, start at time 0. So p at 0 is some p naught. Or dA dt for radioactive decay was a negative kt, where we knew the starting amount of some substance. Okay? Ka, sorry. Are you not getting anything? Let me try again. Oh, it crashed. Well, no. Anything? Yes. Okay. That's being weird. Okay. So let's just do an example here. We've got a population P naught, number of bacteria, an initial condition at time t equals 1 hour. We're told that the bacteria measures to be 3/2 of its starting amount. Okay, so we're starting at P naught. At time t equals 1, we know we have 3/2 of that. So basically we've grown by a half. So we now have 50% more of the bacteria than we started with after 1 hour. If the rate of growth is proportional to the number of bacteria present at time t, we want to determine the time necessary for the population to triple. So let's just do this in some steps here. First of all, let's set up the differential equation along with the initial condition that's provided to us. And then we'll use the extra information to help find missing parameters that we don't know. Okay? So first of all, dp dt would be equal to, just like before, kp. And we also have that p at 0 is p naught. That comes from this statement and, of course, this statement right here. Now, you may be able to eyeball that and know exactly what function solves that. I'm still going to go through the steps to solve it as a linear differential equation. Just 1, to practice solving linear equations. 2, so that whenever you have similar problems to these in your homework but not exactly the same, you know the steps to be able to solve them, right? Again, looking at this, I know the answer is going to have something to do with e to the kp, but I want to see how that unfolds. So let's remember how to solve a linear differential equation. I claim that right there is linear because I can write it like this: dp dt minus kp equals 0. Right? You have a 1 in front of the derivative. You have some function in front of your dependent variable, and then you've got some function over on the other side over here. Okay? Linear. So how do you solve a linear differential equation? Nope, that's exact. You're thinking of the exact stuff. Who's the key player on the
Use a mu to multiply
the mu,
through,
the integrating factor?
which is e to the
Mu
x function.
e to the integral, in this case would be negative k dt.
Right.
So e to the negative kt is your mu. Linear means mu, the integrating factor. And what do we do with mu? Multiply him through the differential equation. So we get e to the negative kt dp dt minus k e to the negative kt p equals
Equals 0.
0. The left-hand side
Equals e to the negative kt
p,
p.
the derivative of that,
Right. And then
because it's the product rule.
I was angry.
So integrate both sides, e to the negative kt p
Equals c.
equals a constant. Right, I jumped a couple steps there, but you make sure you understand. Again, you just recognize that that's the product rule, and then we integrate. So what's P? Just multiply both sides by e to the kt. So now we use the initial condition to find C, which is real simple in this case because you do P of 0, which gives me C e to the 0, which is just 1. And that has to equal from right there, right? P naught. So C is P naught. Are you with me so far? This is all repeat. I haven't done anything new at all. I've just got now P is P naught e to the k t. Question so far?
You just crossed P naught.
I just said that when I plug in 0, are you talking about right here?
Yes.
Right there?
Yeah.
I plugged in 0 for t, right? So I got e to the 0,
So we can,
which is just 1. E to the 0 is 1. So I end up with c equals p naught. So this is my solution equation. Problem is I don't know what k is and I don't know what p naught is. I actually don't need those to answer the question. What's the question we're trying to answer?
Necessary number, or the necessary times the number of bacteria present.
Okay. So let's use the other information that we've got to find something. Okay. What else do we know about this population of bacteria?
That'll be 1.5 times the size after 1 hour.
So if we plug in 1 for t, we should get 3/2 p naught. Use p of 1 equals 3/2 p naught. What is that going to help us solve for?
P naught.
Well, let's see. If I plug it in, that means I get 3/2 p naught. By the way, if you run out of space on this side, I only print on one side so you can use the back side.
Right.
3/2 p naught equals P naught e to the k times 1. Okay, now what?
You separate the K's and the P knots, I guess. Then that's it for something. Anyway.
What do you notice about the P naughts?
They cancel.
If you divide both sides by P naught, they're gone, right? Which would leave me with an equation with only one unknown, which is good news, which means I can use this to solve for
Okay.
k. Divide the P naughts off, and I get 3/2 equals e to the k. So what's k?
The natural log of 3/2.
K equals natural log of 3/2. Let's go ahead and approximate it with a decimal there. What do you get? You don't know that off the top of your head?
No.
And you don't have a calculator just right there in your front pocket with your pocket protector?
Okay.
All right, I'll tell you what it is. 0.4055.
Oh.
Obviously.
My brain calculator was right there on the edge. I almost had it.
Well, you know it's less than 1 because 1.5 is less than e. It's less than half because 1.5 is less than the square root of e, 2.7. Anyway, there we go. So here's what we know. So we know P of t is equal to P naught e to the 0.4055 t, or approximately. I've rounded the k. I could put a log of 3/2 up there and handle it differently. But in most cases, your measurements are going to be decimals in these kinds of applied problems. Still haven't answered the question, though. Question is, how long does it take for the bacteria to triple? So how would you solve that?
Set P naught e to the 0.4 equal
To 3? We don't want 3 bacteria. We want 3 times
3. P naught.
whatever we started with. And what do we start with?
P naught.
And 3/2 P knot.
Well, 3/2 was what we had. 3/2 P naught was what we had after 1 hour. We started with just P naught. So if we want to know how long it takes to triple, we'll set it equal to 3 times what we started with, which was P naught. So notice you now have 3 P naught equals P naught e to the 0.4055 t. Three times the start. I'm just kind of scribbling in some notes here to help you remember some of the tricks that we learned along the way to make sure we can solve these in our examples in our homework. All right, can you solve that for t? That's pretty simple, right? What'd you do first? On this?
Get rid of P naught.
P naught divides out. So 3 equals e to the 0.4055 t.
So natural log of 3
0.4055 t. So t is natural log of 3 divided by 0.4055 t.
or
T. I don't know why I put the t there.
natural log of 2. Wait, no. Never mind.
Okay. How about a calculator? Ooh, a maple calculator. That looks awesome. Not ever used that before. Oh, look at this guy. All right. Okay. Yeah, I need access to the internet to use my calculator. All right, let's do natural log of .40, no, point, was it 3? About .4055. I have no idea what I just did. Should probably use a calculator I know how to use. Fine. Oh, no, I'm
What is
starting.
the equation for that?
Oh, give me a 0? What's that? Alright, sorry. That was stupid. Let's try a regular calculator. Y'all bring calculators with you to class?
Yes, I have my calculator.
2.709.
2.709. And the units would probably be what? Hours, because that was the units we used for the 3/2, or for the 1, I guess, when we plugged in to get that. So 2.709 hours is how long it would take to triple. Okay, so in this example, we've solved a linear model. We have used other criteria when we don't even know how many bacteria there, which, by the way, would make sense, right? If you're measuring how much of a population of bacteria is on a petri dish, you're not going to know how many bacterial cells are on there, right? You're not going to know P naught. Usually, we measure those by area, that is, the actual size of the colony, and we use that to approximate how much is actually there. So we could use that to come up with things like there's now 50% more bacteria after an hour. We know that we have 3/2 of whatever we started with. We want to know how long it takes to get to 3 times what we started with. We've got that option now. All right. Yeah, why not? Let's go ahead and graph some stuff in Maple. I'm going to release the computer, and I am going to ask you to open up Maple on your own. And we're going to refresh our skill set on graphing things in Maple.
Maple 15?
Yes, Maple 15. Now, it really doesn't matter whether you open a document or a worksheet. I personally always open worksheets because I think old school, like Maple was in the good old days, 10 years ago. But you can do the same thing in just a document. I want to plot my solution. So remember, my solution was P naught e to the kt. So here's how I'm going to do. I'm just going to plot by typing the plot command. And the arguments I'm going to give it is the function and then a range for values of t. In the example, the first one I give you there is if your P naught was 1,000, just to pick a value. This will allow us to see the scale over time. EXP to do e to a power and 0.4055 times t. Here, I'll blow this up so you can see it a little bit better. That right there is 1,000 e to the 0.4055 t, comma, and give t a range of values. Let's start at 0, and let's go at least to 2.7. So let's go maybe to 5 hours. And then hit enter. I'm going to actually give us a range of my y-axis as well. I'm going to go from y equals 0 to 8,000 so I can see the 0 on my y-axis. Okay, so nice exponential curve, exactly as you expect, and you can kind of see if I'm asking how long does it take to triple in size. So if you start at 1,000, how long does it take to get to 3,000? If you draw a line straight across, that confirms the estimate that we got of 2.7, right, is about when we hit 3,000. You can see that from the graph. The other thing you can see from the graph is whenever you've got a positive k, you see exponential growth. If you went on to problem 2, and you typed in a negative value for k, namely 0.528 was the one number I gave you. But I'm going to turn off the y, or sorry, I'm going to delete the y range for now, just to see what the default range looks like. That should be point, yes, right there.
How do you get the little red arrow?
Do what?
I wrote that all out, so I didn't get the red arrow.
I just hit enter at the end of my line.
I got unable to match the delimiter.
That usually means you're missing a parenthesis.
That's, there's something about syntax and stuff.
You got to put the parenthesis at the end of the 8,000, Jeremiah, on yours.
Oh, all the way at the end of the
Yeah. So you're issuing a plot command.
Oh, got it. Okay.
So this parenthesis at the start matches the parenthesis at the end.
How do you usually put them in?
You type
Just
plot
like
and then parenthesis 1,000 times exp. All right. Who else was having trouble, Dylan? Where are you?
Can I see what it is?
Oh, don't type the greater than sign at the beginning.
Okay.
That's on worksheets. It always puts that at the beginning. So if you delete that, it'll be fine.
Is it times 2?
Now I haven't entered yet on this one, but if I do now, the difference is what? What happens when your constant is negative? As you go from left to right, the function is now decreasing and it's approaching 0 over time. So the first one was a 0.4055. If I do that a second time, I'll just compare 5.528 with a negative out front. Those are the two different graphs that I get. So the k in the problem, positive or negative, makes a difference as to what direction the curve is going to go as the system evolves. The dot between these two, in case you didn't see me type those, that's just shift 8, right? That's the asterisk to get a times in between those two.
I'm not doing like all this. I'm all well. No, it's working. It's starting at 8,000 rather than 1,000.
But yeah, because you're telling with
got
t equals 0 to 5 and y equals 0 to 8, that is giving your window parameters.
Mine is not plotted.
Alright, let's see. What is going on with yours? You need 2 dots between those. You only have 1. And you had a space between plot and the parentheses, which you can't have. There you go, Christian. Okay. All right, let's let's keep moving on. Let's do another couple of these. I think we can knock these out pretty quick. So now that we've seen what the graphs look like, the next example is an example of a radioactive decay problem, which we will solve in a similar way, but turns out that your constant is going to be negative in these. So I'm going to come back here. Do you want me to broadcast, or do you want to keep Maple open? Up to me? Taking over. All right, a breeder reactor converts relatively stable uranium-238 into the isotope plutonium-239. After 15 years, it is determined that the amount remaining, actually only 0.043% of the amount has disintegrated. So a very small amount has decayed from uranium to plutonium.
Wait,
I think I've stated this wrong then, or I'm misreading this.
do you mean uranium?
I think I mean uranium here. Let me double check. Well, I can't. I didn't bring my book with me. I stole this problem out of the book, but I haven't looked at it in a while. So we're starting with uranium and we're decaying to plutonium. Right?
Yeah.
So we're starting with A naught of uranium. It's decaying into this isotope. We want to find the half-life. And we're going to use it using we're going to find it using differential equations. Now, any decay or growth problem now, we can jump straight to the solution. Because we've already solved this, right? The rate of disintegration is proportional to the amount remaining, which tells me dA dt is equal to K times A. And I put a minus sign out in front of the K, will give me this if I go through the whole steps that I did before, right? So I'm going to skip straight to that this time and say I know the solution to the differential equation. Now, let's find out what we know to figure out the answer to this question. We want to know the half-life. It's basically the same question we just answered. Last time we said how long does it take for it to triple, so we set it equal to 3 times P naught. Now we want to know how long does it take for us to end up with half of what we started with. So we'll set it equal to half of P naught. But first, we need to use this extra information here to find K. Okay? So solve for K. And here's our solution. We're going to take the A naught e to the minus kt, and what are we going to set it equal to?
Didn't we determine it was positive?
Well, what I did was, since it's decay, I stuck a minus sign here, so that minus sign shows up right there. I replaced k with minus k. So on the previous problem, we were doing growth, right? It was getting larger. So it's the difference of this problem versus this problem.
But when we solve for that, doesn't it, because we integrated and then divided,
So it went, yeah, so we ended up with a positive k here, right? E to the kt when we started with kp. If we replace all the k's with minus k's, then I end up with a minus k there.
Oh, because, okay, yeah,
Yeah.
after we divided.
Exactly. All right, so what do I set that equal to? Actually, I guess I need to be more careful. This right here is after 15 years, what is that equal to?
0.00043.
Well, that's not how much is left. That's how much was disintegrated. So how much is left behind?
0.00057.
1 minus
0.957?
0.0043 is left, right? Which would be 0.99957.
Yeah.
I realized what just
Do you see why I'm doing that? Okay, so 0.4, I moved the decimal place twice to actually get the amount. 0.00043 A naught is is converted. So, the amount left is 1 minus that times A naught. Right? If 0.00043 times A naught decayed, then the amount that you have left behind is 0.99957. Does that make sense?
Yes.
Okay. Now, can you solve that for K? A naughts divide out. You have the natural log of 0.99957 equals negative K. It's 15. So K would be the negative natural log 0.99957 divided by 15.
So K equals 2.867 times 10 to the negative 8.
All right. So just plug that in my calculator. So now I have that A of t is A naught e to the negative 2.867 times 10 to the minus 5 t, or 0.00002867, or 2867. 4 zeros in there. Now find half-life. Set A of t equal to 1/2 A naught. And solve for t. Because that's how long it takes to get half of what you started with, right? So 1/2 A naught equals A naught e to the minus 2.867 e to the, I won't use e, times 10 to the minus 5 t.
How come when you solve this, you get a negative number for t?
You shouldn't.
Well, because
Keep that minus.
natural log of both sides, and you get natural log 1/2 equals.
And natural log of 1/2 is negative. Anything less than 1, the natural log is going to be negative.
Oh, I didn't bring negative.
Right. So you do get t is equal to natural log of 1/2 divided by negative 2.867 times 10 to the minus 5. I'll use a real calculator this time. Okay, so 1 divided, well, just type in
4.3.
natural log of that's negative divided by a negative 2.867. Where's my 10 to the power thing? That's not it. That's just raising 10 to the power.
It's just the inverse log.
Yeah, I don't want that. Where's like the scientific notation button on this calculator.
There is none.
Dang it. How about 0.0? What the? Oh, God.
It's 24,000.
Where's a calculator when you need it? 24,000?
174.36.
174.36. I need a real calculator. I need to bring those with me. $24,174.36 years, based on the information provided.
So we should be using nuclear power. And it's a lot
Well,
easier
the-
than minerals.
Yeah.
Nuclear power.
Except that the problem is the thing that we decay into is also still radioactive, which also has an enormous half-life, which means our waste needs to be taken care of. Now, I'm not saying I'm for or against nuclear power, but you've still got a waste problem to deal with of radioactive
We
waste.
can
Send the
get it
waste.
to nuclear decay and then
Send it to space or bury it in Nevada, one of those two, right?
What happens when the rocket blows up?
Put it in a barrel
You're
and
going to
go out in
space.
space and just kind of shove it.
But what if the rocket blows up?
once rocket exploding is less of a variable and slightly safer to launch
Whenever
into
it's
space.
zero.
Yeah, although
If the rocket burns.
it's the same
Yeah.
way that reason they
rains
put
down
nuclear
over-
propulsion on rockets is because
If we could get like a space elevator design
That's not
and
bad.
then launch from the orbit up there, we got much
Or we can
less
just
water.
store it in the
A space elevator,
That's where you put, a cable that connects with a
Yeah.
geo
and if you put a space
stationary orbit object up there, and you just move it up and down the cable instead of having to launch to get to the.
and once you create a
Geospatial
space
orbit.
elevator, all you have to do is get it like halfway out the earth and then essentially just throw it out there to space.
Or you can just put it on like other balloons.
No, like,
Go up. It's not gonna explode.
Man, we've solved the world's energy
We've
crisis
done it, yeah.
in here
It'll
today.
just be right in our upper atmosphere, just waiting to
Yeah.
fall down.
Exactly.
Kill all of
That's why when somebody-
Let's do a law of cooling problem and a mixture problem before you have to tackle these on your own.
Great idea.
Basically, what these problems are, they're a lot of using additional information to actually answer the problems where you may not be given the K, right? The K of the constant proportionality is not something that you know in advance in any of these problems, but you can use empirical data to solve for K. In the previous two examples, we used what proportion we had remaining or what proportion we had after a certain amount of time. We were able to find K and then answer questions based on that. In this case, we have this Newton's law of cooling problem where we know that the temperature of the object is changing proportional to how far away it is in temperature from the surrounding medium. That's the given assumption with Newton's law of cooling. So, how do we find the K? The K is can be determined by taking one additional temperature measurement and setting the solution equal to what that temperature measurement would be. Like in this case, we know we have the formula for the Newton's law of cooling. We assume we are giving an initial temperature, and we know what the surrounding medium temperature is. In this case, we take a cake out of an oven, and the cake is 300 degrees when we pull it out. 3 minutes later, the cake is 200 degrees. We know that the room temperature is 70. We want to know, can we figure out what the temperature is over time? That extra piece of information, the 3 minutes later at 200, that is T at 3 equals 200, will help us solve for K. But first, we have to actually know what the solution for T is. Okay, so step 1 will be to solve the IVP. Step 2, find K. Step 3, answer the question, which is how long does it take to get all the way down to 75 degrees? Right? In that case, we would set T of T equal to 75 and solve for T.
Just curious. I don't know. I can't see the cake getting lower than the room temperature. Can that happen actually realistically?
No,
The room temperature is 70,
Exactly. But
and how long does it take to get to 75?
for the room or for the cake?
The cake. The room is not changing.
Oh,
We're assuming
wait.
that the cake does
For
not
some
affect the
reason, it
temperature
reminds me
in the
the
room.
temperature is lower than 70.
Okay.
I don't know.
Right, so the cake will not get lower than 70,
Yeah.
but 75 is still above 70, so yes.
Although I'm pretty impressed, 3 minutes for the whole cake to be like an average temperature.
100 degrees cooled off. It's actually not unheard of that it cools off that fast.
In 70.
And it depends on, I mean, obviously there's some parameters we're not taking into account. Shape of the cake, right? Shape of the cake, the what kind of cake, and you know the actual, well, not what kind of cake it is, but that you're cooling a cake versus cooling, say, a hot ball of nickel. You know, like the guy that,
Oh.
you know, the guy that places the
Very few molecules of air
heated
in
ball
those
of nickel
releases.
onto all kinds of different electronic devices, and this is what happens to them. There's the YouTube videos for those. So the substance itself, the shape, will make a big difference, right? Obviously, that's why whenever you crack open a computer and you see the chip, you've got these cooling fins, the heat sinks on the back of them to help pull away the heat that's being generated by that processor, because surface area is the biggest determining factor of how fast something cools off. The second biggest, or maybe, I don't know if it's bigger or not, it's the medium itself and then the surface area. Those two things are major factors in how fast something cools off, right? So we can answer everything we need to with this question with the information provided.
Does Newton's law of cooling take into account, like, the cake's warming up the room as well?
No, we're assuming the medium stays constant. We're assuming a uniform temperature of the object itself. So there's a lot of assumptions we're making that we could make a much more complicated model. And heat flow is a very difficult problem in general to solve that's beyond the scope of this class. You need partial differential equations to handle that problem.
No thanks.
Those going into engineering, you could see that.
I like it though, that math class.
Yes. Well, yes and no. I mean, there's formulas already been developed to be able to use those to solve the problem in certain cases. Let's just solve the problem, shall we? dt equals k times, what's t sub m?
300. Wait, no, 75. 70.
Minus capital T.
Okay.
And t at 0. In this case, we actually know it. This is something we can measure. 300. All right, so we start by solving the differential equation. It's linear, but it's also separable.
Yes.
How do you want to solve it? You want to solve it as a linear or as a separable?
Separated, which I assume is the more complicated version.
It's, to me, it's easy. It's the same both ways.
I let this separate the since we did linear.
Oh, okay. So we'll do, for variety's sake alone, we'll use it as separable. This variety of the spice of life. So to separate this differential equation, I'm going to move the dt to the right-hand side, and I move the 70 minus t to the left-hand side. So 70 minus capital T on bottom equals k dt. You could just as well have done this on the previous example. You could also multiply out the k and move the minus kt to the left, and then do the linear stuff. This gives me, if I integrate both sides, the right-hand side is easy. Actually, both sides are relatively easy. But what's the right-hand side?
KT
KT
plus
plus log of C. Just because. You know how I feel about manipulating C's. They're very manipulative. On the left-hand side, what's the integral of 70 minus 1 over 70 minus t? Natural log of 70 minus t, but with a minus out front. That should be capital T there. Why a minus out front?
Because of the 70? Or because of the minus t.
because the minus t, because the chain rule,
Oh yeah, you must go.
or if you did substitution, the minus sign shows up. Just think about it. If I had to take the derivative of the left-hand side, I better get what's up here. Right? The derivative of natural log of 70 minus t better be 1 over 70 minus t. But when you take the derivative of the natural log of 70 minus t, if I didn't put the minus sign right there, it would be 1 over 70 minus t times the derivative of what's inside. Chain rule. And what's the derivative of 70 minus t? Negative 1. So I have to have a minus out here to correct that so I get a positive up here. Does that make sense? Okay. Or you could do u equals 70 minus t. du becomes minus dt. So you got to put a minus here and put a minus out here. And that's another way the minus can show up. All done. Now then, I'm going to move the minus over the other side and say natural log of 70 minus capital T equals minus kt. I guess technically that's minus log of c, but minus log of c is positive log of c. Now take the exponential of both sides.
Oh, that's right.
70 minus t equals, and since I now have a plus here, I can do it as times. All right, e to the minus kt, e to the log of c. Those cancel, and I get c e to the minus kt. The only time I really include natural log of c on the right-hand side is if I know the left-hand side is just going to be the log of something. That way I'll know I can be able down here to cancel that out and get my c. I was just planning ahead. So then what does t equal if I solve that for capital T? Should be 70 minus c e to the minus kt. You can just move this to that side, move the t over here, flip it around. You've got capital T is 70 minus e to the minus kt. So there's your solution to the differential equation. Now what?
Use the initial value properties.
Right, so
Okay.
t of 0 is 300. So 300 equals 70 minus c e to the 0. So actually I can just not even write that part, right? So c is
Negative 230.
okay. So the solution to the IVP is t of t equals 70 plus 230 e to the minus kt. I'm going to block that off so I can find it easily. Now, I still can't answer what happens or when does it get to 75 until I know what k is. Okay? So that was the end of step 1. Now step 2 is find k. And how are we going to find k?
When t equals 3.
T of 3 equals 200.
Yeah.
So 200 equals 70 plus 230 e to the negative k times 3. So subtract the 70, I get 130. Then I can divide off the 230. I'll do that in 2 steps. 230 e to the negative 3k. So 130 divided by 230 equals e to the negative 3k. take the log of both sides, so log of 13 over 23, and cancel the zeros. Or divide 10 out of the top and bottom, equals negative 3k. So k is the natural log of 13 over the natural log of 23 divided by negative 3. Actually not, sorry, that was sloppy. Natural log of 13 over 23, that would be natural log of 13 minus the natural log of 23, actually.
Right.
.19. So that means T of T is 70 plus 230 e to the negative 0.19 t. Now we can finish the problem. Set T of T equal to 75. Solve for T. $75 equals 70 plus 230 e to the negative 0.19 t. We end up with 5 over 230. So natural log t is the natural log of 5 over 230 divided by negative 0.19.
And it's 1 over 46.
Okay. Take the log of that and divide by negative 0.19. Or whatever the k is that you got before. If you had more decimal places still in your calculator, you can use that.
So T equals 20.13.
Minutes. Beautiful. By the way, the last question. I mean, it's kind of interesting to note before I even mention the last question. It only took 3 minutes to drop 100 degrees, right? It takes a full 20 minutes to drop all the way down to 75 degrees. It's going to fall slower and slower, right, the further out you go. At the same time, that last question of how long does it take to reach room temperature? What's the answer to that one?
A while.
You just plug in 70 to the left side.
Set it equal to 70,
Solve.
you'll have a problem. Right? If you put 70 on the left-hand side, you actually end up with 0. Well, I'll just do it. 70 equals 70 plus 230 e to the minus 0.19 t. Problem is 0 equals e to the negative 0.19 t. It's asymptotic. It actually never reaches it. It becomes, however close you want to get, eventually it will become that close, but it will never actually equal 70. So mathematically, the answer is never, right? Practically, well, it's within some measure of noise, right? Whatever your device is that you're using to measure the temperatures, or whenever you're thinking about the fact that you've made this assumption that the cake is uniformly the same temperature all the way through, eventually you get to the point that the real world kicks in and your model no longer makes sense. So it's not that it actually never reaches that temperature, but mathematically speaking, it never does. All right, let's set up the last problem. Let's do one mixing problem again so you can see this one more time.
Are these, for the most part, like, you could switch in some numbers, but are they always going to be the same equations? Like, when we solve for t sub t, 7 minus t negative kt, dt?
Yes and no. I mean, I can throw some more wrinkles at you than just switching numbers,
Yeah.
but they're very similar. Okay. In fact, so the rate of growth problems, the decay problems, it's just a difference of how I ask the question, what data that I give you. So instead of giving you specific data points, I may change the way that I phrase that. So you've got to think a little bit critically there. But in the end, all of the strategies in this section are about using a model that we already know what the differential equation looks like, where we already know the initial condition. But now I give you additional information that helps you solve for those unknowns in the problem. Actually, the mixture problem that I'm going to give you here, I've given you everything in our previous examples. We just didn't get to the step of solving it. There was no unknown k or other unknown parameter generally in our mixture problems. So we've got a large tank, which I'm going to represent with a box. We've got something coming in and something going out. The large tank contains 300 gallons of brine, so the volume is 300 gallons. The salt is entering through a solution, the tank, and it's leaving the tank. The brine solution being pumped in at a rate of 3 gallons per minute, mixes with the solution inside here, and then leaves also at a rate of 3 gallons per minute. The concentration of the salt coming in is 2 pounds per gallon. The amount of salt initially in the tank is 50 pounds.
So the initial concentration is 1/6.
Yep. But the concentration that's leaving is not a fixed number. It now depends on time because the concentration will change over time. So remember, this is what I called flow. This is what I called concentration. So this here is flow. The concentration leaving is always going to be the amount over the volume, which the volume is not changing. So this piece right here, I had to know how to find. Right? That's amount divided by volume. But A is changing over time. Remember that dA dt in these problems is rate in minus rate out, where rate is flow times concentration. So that means dA dt would be, what's the rate coming in?
6.
6. And the rate going out?
A over 100.
3 times A over 300 or A over 100. And then A at 0 is 50, so there's your initial value problem. In case you didn't see that, that's 2 times 3 minus 3, or A over 100 times 3. Guess I'll write it in the same order. 3 times 2, and then 3 times A over 300. That's how I got that. So here's the problem that I've got to solve, is that one right there. Let's use the linear approach. Instead of the separable. We could do either one, but I'm going to use the linear approach.
dA dt plus
dA dt plus
A over 100 equals 6.
equals 6. And I just wrote the 1 over 100 out front to point out the fact that that's just a coefficient. that I'm going to use to calculate my mu. So mu is e to the integral 1 over 100 dt. Can I just do 0.01? Does that work for you guys? So 0.01 t. So multiplying the integrating factor, and I get e to the 0.01 t dA dt plus 0.01 e to the 0.01 t times a equals 0.06. No, that was no 6 e to the 0.01 t. I don't know what I was smoking there for a second. Now the left-hand side is d dt of e to the 0.01 t times a equals 6e to the 0.01 t. Recognize that it's the product rule on the left-hand side, and now integrate both sides with respect to t. You get e to the 0.01 t times a equals
6e to the 1 t over 100. Let's see.
it's actually 6 divided by the 0.01.
Right.
Which 6 divided by 0.01 is actually 600.
Yes.
I'm going to multiply through by e to the negative 0.01 t. And I get a is 600 e to the 0.01 t times e to the minus 0.01 t is just 1 plus c e to the negative 0.01 t.
So you multiply by e to the negative 0.01.
Yeah, so I multiplied each one of these terms here. This one, and this one by e to the negative 0.01 t. So on this one, it cancels out, right? E to the negative 0.01 t times e to the 0.01 t is e to the 0, so that's just 1, so I just get a. Same thing on this first term, 600 times 0.01 e to the 0.01 t times e to the minus 0.01 t is e to the 0, so just get 600. And then c e to the negative 0.01 t. Next.
Use the initial value problem to solve for c.
So a at 0 is 50. So 50 equals 600 plus
c.
C is negative 550. So A of t equals 600 minus 550 e to the negative 0.01 t. We now have an equation to model the amount of salt over time.
How much salt is in the tank after a long time?
So that's a vague question, except that you have an idea of what that means. What do I mean when I say, what happens after a long time? What am I really asking you mathematically to do?
Is it going to zero or?
Yeah.
What is it?
What is it approaching? What's it converging to? So take the limit of this thing as time goes to infinity. Okay? So what is the limit of a of t as t goes to infinity? What happens after a long time? What's the behavior of this thing? The limit as t goes to infinity of 600 minus 550 e to the minus 0.01 t. What'd you say?
Isn't it just 2 pounds per gallon?
Well, that's the concentration, but we want to know the actual
5.5 amount of salt.
amount of salt. What happens to this guy as t goes to infinity?
Goes to 0.
It goes to 0. Right? As you raise it to a larger and larger negative power, e to a very large negative power is very close to 0. It's like dividing 1 over e to a very high positive power. E to a high positive power gets big. So you're dividing 1 over something very big. Goes to 0. So what does it go to? Careful. 0 times 550 is
600.
0.
Oh, the entire thing goes to 0.
Which would mean this has to go to 0.
That makes sense.
If the part with the t in it goes to 0, then 550 times it also goes to 0. Which means I get 600 minus 0, or 600
600 pounds.
pounds. Right, amount is in pounds.
2 pounds per gallon.
Which is perfectly obvious what the answer should be, right? Because if you go back up here, I'll scroll back down in a second, if it's always 300 gallons and the thing coming in is 2 pounds per gallon, eventually it's going to approach what the concentration is that's coming in. So the concentration will eventually become 2 pounds per gallon. If there's 2 pounds for every gallon and there's 300 gallons, that's 600 pounds. Okay, but now you see the behavior. Now, where I will throw a wrinkle in this problem is I think one of the problems, I changed the concentration coming in to be a function of t. It varies over time. It oscillates. Now, where does that affect your problem?
Where it is at that time.
When you build the problem, remember, rate in minus rate out. It changes one of the concentrations, so this will have a t in it. Okay? So the right-hand side of this problem may have something with t's in it. You still use the linear approach, but now your solution is going to be much less boring. Be more interesting. I was going to say hard, but challenging. I don't know. You have what you need to be able to work the problems in the homework, and I strongly encourage you to work the problems before class on Thursday and ask me questions on the one you're stuck on, because you will get stuck on a couple of these, and I need to know which ones they are. I know the deadline is not till 11:59 on Thursday, but I won't know which ones to help you with if you don't tackle them before then, before class. Okay? Otherwise, I'll just keep moving on, and we'll do nonlinear problems next.
So are they emailing you a copy of that test?
I haven't filled it out yet. I'm going to go fill that out.
Okay, because I didn't
today.
know, because they're like...
More than likely, they'll send me a link to where you log in, and they'll give me a password. If it's anything like what we do with our online stuff, it's I get a password and you log in. Now, do you have where you log in to do all the work for the class?
Blackboard, that's what it is. But I mean...
So the way that we do it here, whenever we have a third-party proctor, after everything gets approved and they say that person can do it, we send them the password to the test. So like you could try to open the test, but you wouldn't know the password. So you come in, you sit at a computer, you go log into your class, you go where the test is, you open it up, but to open the test you have to have a password. I type in the password and then watch you take it.
Well, for that I'm just confused because it says no computers during the test. Only because I was assigned a pencil. I'm like, are we
Okay, well, I mean, we do that with our math tests online. They're different. We don't actually have the math tests that we give on the computer. So if that's the case, then they'll email me a link to the test, which I can then download and print and make you take. And then I would scan and email it back. We do that too.
Physically mail it to them.
I will drive down there and put it in their hand. Okay, so that entire conversation is now